Hey guys, we're going to continue on with impulse and momentum. I think we left off with the Archer question, which was at slide number 8. So this is starting on slide 9. Actually, your slides are different than mine, so never mind. Just find the one that says impulse and momentum. Like we learned today, we know that momentum is simply when I have mass times my velocity. We know that momentum is a vector quantity because velocity is a vector quantity. So momentum depends on direction, and it will be in the same direction that the velocity is acting in. Now, we also talked about the conservation of momentum, of linear momentum, and we know that that conservation of linear momentum is where I have the change in momentum, and specifically the total change in momentum, is equal to 0. So I can say that my initials, so let's say I have P1 and P2 initially, the momentum of both of them initially should equal the momentum of both of them finally. So I could say either one of those things, and that would indicate my law of conservation of momentum. Okay, so let's get into what happens if, because all of those things that we talked about today were if we had an isolated system. What happens if we have a non-isolated system? So the momentum of a system will change if a net force from the environment acts on a system. Okay, so the momentum of a system will change if a net force from the environment acts on a system. Because isolated systems are assuming that there are no net external forces that are acting on a system. So I don't have energy crossing over the boundary from system to surrounding or from surrounding to system. But in a non-isolated case, that's not the same. So in a non-isolated case, we do have a net force that's acting on the system from the environment. So if momentum is going to change, a net force must be acting. So for momentum considerations, a system is considered to be non-isolated if this net force, so we'll say if a net force acts over a time interval. So a system that is non-isolated, and if we're thinking about its momentum can change if a net force will act in some certain amount of time. Okay, so because of this, I'm going to erase these things. We know that momentum, well actually let's go back to what we talked about today. We knew that force was equal to mass times acceleration. That's Newton's second law. Well, I also know that acceleration is equal to dv over dt, so I could say force is equal to m times dv over dt. So then I could, maybe if I bring out force is equal then to, if I'm looking at my mass and my velocity together, we know that mass times velocity is momentum. So because I know that my mass and velocity is momentum, I could say that then the rate of change in momentum over time is also equal to force. So we talked about this today in class, but now we can get this. Knowing that mass times velocity is momentum, I could say that the force would then be equal to dp over dt. Let's say, though, that now I want to not have this solved for force. Let's say I want to have this solved for dp. If I do that, I would have force times that time interval dt. And if maybe I have more than one force, I can even be more specific by saying that dp is equal to the sum of the forces, all of those external forces that are acting in a certain time interval. So when we say that, when we're talking about that for momentum considerations, a system is not isolated, if we have a net force that's acting over a time interval, that's what we mean when we say this, that my momentum is going to be somehow changed based on my net force that's acting in some time interval. This momentum equaling my sum of the net forces externally in that time interval has another name, which is called impulse. An impulse is simply, I'll write it down here, impulse is simply the force acting on an object. So it's the force acting on an object over, we'll say delta t, over a time interval. So it's the force acting on an object over a time interval. That's impulse. Now, as that time starts to approach zero, let's say that we have two things that are going to collide with one another, and I want to know the net force that's acting maybe like right at that, maybe right at a collision. Maybe I want to know about friction. Then as time approaches zero, or as time gets closer and closer to zero, I could say then that impulse, which we will symbolize with a capital I, and it is a vector, so we'll make sure that we have our arrow above that. So impulse can also equal, since time is approaching, we can integrate from maybe like, we'll call this an initial time to a final time. So there are my bounds. And then we can say F dt. Because impulse is all about a net force that's being applied in a specific time interval. So I can integrate if we're thinking about as that time is approaching zero, as we're getting closer and closer to just getting that net force, that net external force, I can find impulse. And this integral is called the impulse, again, just the net force over a specific time. Okay, so we can also find impulse based on just using a time averaged force. So if I want to say that, I know impulse is equal to the sum of my forces times my change in time, that time interval. We'll probably see this one used way more frequently than the integral version, just because this one we can do really quickly on the multiple choice test. So if we're looking at our graphs here, we can see that if we have a constant force versus if we have the impulse imparted to a particle by a force, we know is just the area that's under that curve. So we can find that. We think about, that's the same thing as when we did work done by a varying force. We also thought about the integral version of the force times the displacement times cosine theta. So same similar concept here with impulse. But the time averaged net force, so doing this way, will also give us the exact same impulse, even if we did one with a time varying force here. So this area, if we use time averaged, so this formula, should equal the area that's under this curve based on the integration version as well. Okay, so this equation expresses or brings to light something that we would call the impulse momentum theorem. So the impulse momentum theorem. And the impulse momentum theorem states that the change in the momentum of a particle is equal to the impulse of the new force that's acting on that particle. So I could say that change in momentum, so delta P, equals impulse I. That's the impulse momentum theorem. Now, we know that momentum has units of kilogram meter over seconds. Well, what units does impulse have? Well, if these are equal, it should have the same. We know that impulse is equal to the sum of my forces times the time interval. I know that force is measured in newtons. And I know that a newton is equal to a kilogram meter per second squared. Well, then I also then know that impulse is also multiplied by a change in time. So I'm going to take a newton and multiply that by, let's say, a second. One of these seconds then, that cancels. One of those seconds will cancel. So then impulse will have units of kilogram meter per second. So the same as momentum. So because of my impulse momentum theorem, we kind of think about this, guys, as also just being another way that we can state Newton's second law. So let's write here, this is just another way to express Newton's second law. Remember in class today we talked about how Newton, when he was talking about his second law, really meant not necessarily mass times acceleration, but he was really talking about the momentum. He was really talking about mass times the velocity of which something was moving. So our impulse momentum theorem is really trying to relate in Newton's second law, especially when we're talking about impulse in the terms of a force that's acting on a particle. So this is mostly just a general statement of the principle of conservation of momentum. So oftentimes we know that our principle of conservation of momentum is just momentum is ultimately conserved. But this is another type of kind of subcategory of our conservation of momentum, in that my change in momentum is also equivalent to the impulse of a force that's acting on a particle. Okay, so in many cases, one force acting on a particle will act for a very short time, but it's much greater than maybe any other force that could be present. So a lot of times when we talk about impulse, we think about something called the impulse approximation, and we just assume that this is something that's true. Now, usually this impulse approximation is something that will be helpful for us when we're analyzing collisions, and we'll probably talk really a lot more about this when we're analyzing your data from your lab. We'll do maybe a couple calculations with impulse. I may throw that in there. When we talk about this particular force, the force of one particular force acting for a short time but greater than the strength of all of the other forces, we call this the impulsive force, which should make sense. It's all about impulse, so impulsive force is going to be this force that's greater than any other force present and is acting for just a very small amount of time. So let's say, for example, that we have a baseball and we strike that baseball with a bat. If we think about the collision between the ball and the bat, maybe like 0.01 seconds of the actual collision time, that time is so incredibly short. And we know that the average force that the bat exerts on the ball in this time is probably going to be, it'd probably be like several thousand newtons. Because that contact force is so much greater than the force of gravity that's acting on the ball or on the bat, we can say that the impulse approximation justifies us ignoring gravity, and then we can just focus on the impulsive force, which is the bat striking or colliding with that ball. So that would be an example of where we can get this impulse approximation, meaning that kind of forgetting about all of the other forces that are acting on it, because really the greatest force that's causing maybe a change in direction is this impulsive force. Okay, so we know that we have momentum before a collision and we'll have momentum after a collision. So I can say I have momentum before a collision, so we'll call that P sub I, and I have momentum after a collision, we'll call that final, so P sub F. And ultimately we're representing these as momenta, and this would represent something immediately before the collision. So that would be my P sub I. That's my momentum initially, and then immediately after the collision. And that would be my P sub F, that momentum after the collision. Okay, so let's look at an example here. Let's say that in a particular crash test, a car of mass 1,500 kilograms collides with a wall as shown. If the collision lasts 0.150 seconds, find the impulse caused by the collision and find the average net force exerted on the car. So first of all, I want to think about all the things that we know. We have a mass of the car, so mass is equal to 1,500 kilograms. I know that initially, so I know VI is a negative 15 meters per second, and I know that my final, after the collision, it's going to be moving in a positive direction, 2.60 meters per second. I also know a time interval, delta t, that equals 0.150 seconds. First part they're asking me to find is find the impulse. Okay, well, according to my impulse momentum theory, I know that impulse is equal to the change in momentum. And I know that my change in momentum is equal to the final momentum minus the initial momentum. Because remember, our change in just means final minus initial. Well, I could also simplify that down and know that final momentum is just going to be the mass times the final velocity. And then my initial momentum is just going to be mass times initial velocity. All of those things right now are equaling impulse. Well, I know mass, 1,500. I know the final velocity was 2.6. I know, again, my mass. I know the initial velocity was a negative 15 meters per second. So in this case, I have all of my variables to find I. So if you plug in numbers, we should get our impulse here to be, I'm going to write it up here, 2.64 times 10 to the fourth. And remember, think about units here would be kilograms times meter per second. So I'll let you plug that in and you can solve if we have questions. Okay, the next part of that says, let's also find the average net force exerted on the car. Well, I now know impulse, and I know that impulse and force and time are all related because I know that impulse is equal to, if I'm thinking about the average net force, close that door for me. I know that the average impulse, or I know that the impulse is just based on that average force times time. Well, I know this is 2.64 times 10 to the fourth kilogram meter per second. I'm trying to find that force, and they gave me time, 0.150 seconds. So times 0.150 seconds. So now if I divide both sides by my 0.15, I'll get my average force. If we do that, then our force should equal 1.76. Let me solve this. Our average force should equal 1.76 times 10 to the fifth. We have force, so that would be newtons. All right, guys, so let's continue on. We've really talked about this quite a bit in terms of collisions. We know that collisions may be the result of direct contact. The impulsive force may vary in time in many complicated ways. So if we think about collisions, we know that momentum should be conserved in a collision. And the collision, doesn't need to include physical contact between the two objects, because, for example, we could have our collision happening between subatomic particles. So let's say right here, I have a collision that's mostly just between the forces that are acting on those particles, and that collision is still considered a collision where momentum is still conserved. So it doesn't necessarily have to include physical contact. As long as there are forces that are still between the particles, we can still have a collision. Typically, we think about the term collision representing an event during which two particles come close to one another. So it doesn't mean there has to be physical contact. So collision just represents particles in close contact. Close contact with one another. So we can have contact like we see here in A, or we can have really close contact in terms of just force fields. We talked about before types of collisions. We know that in an elastic collision, perfectly elastic collisions will occur on a microscopic level, and in macroscopic collisions, there's only approximately elastic collisions occur. And that's because we're always going to lose something, usually in a collision in real world. We may lose something to sound, we may lose something to heat, we may lose something to just deforming, like if we're thinking about our car, typically our cars are smashed in, so we have some matter transfer that's happening. These collisions are described by an isolated model, so we typically think of elastic collisions as having my kinetic energy conserved, and we also think about our elastic collisions having momentum also being conserved. So to be an elastic collision, kinetic energy must be conserved, and that change in momentum must also be conserved. Now, this is different from an inelastic collision, because in an inelastic collision, the objects will stick together after the collision, and if they stick together, then we call that a perfectly inelastic collision. In an elastic collision, what will happen is that they will collide and they will bounce off. So in an inelastic, they'll stick together. If it's perfectly inelastic, they will stick together. If it's not perfectly inelastic, you may have they may collide, they may stick, but then ultimately you may have a little bit of bounce off. All right, guys, we'll finish up the video here. I will see you guys tomorrow in class. Bye.